Thanks for the introduction and thanks for inviting me. Today I'm going to talk about a new work that I'm really interested in. It's called Guarantees for Tuning the Step Size Using a Learning to Learn approach. So this is joint work with my students, Wang Xiang, Yuan Shuai, and Wu Chenwei. All of us are from Duke University. Right, so what do I mean by a learn-to-learn approach? So let's first think about optimization for neural networks. So in optimization for neural networks, of course, we all know that neural networks recently have achieved a lot of success in learning all kinds of machine learning problems. You can do image classification, image segmentation, or you can also do reinforcement learning, apply it to games like Go. But with all of these success, how do you actually achieve that? So if you were a student, you might want to know, how do you actually train a neural network to perform all of these amazing tasks? So how do you train the neural networks? And you might ask your advisor, and you might get this simple answer, right? It's easy to train neural networks. You can just use a very standard optimization algorithm, such as stochastic gradient descent, or using Adam, or there are just really only a few of algorithms that people recommend you to use for training neural networks. So it seems really simple, right? All of these algorithms are also implemented in these deep learning frameworks like TensorFlow or PyTorch. So you can just write your code for your network, apply the standard optimizer, and hopefully very magically things are trained correctly. Unfortunately, that's not quite the story if you are trying to train neural networks for some new tasks that you have designed. Once you look into how training works, there are actually a lot of things you need to change. For example, for stochastic gradient descent, you need to change the step size. You need to decide whether you use a momentum, although it's typically recommended. You need to think about whether you want to add a weight decay for regularization, whether you want to use batch normalization. Unlike the optimization algorithms, which there are only a few of them, there are tens of these tricks that you can choose from, and whether you use any of them can change the performance of your final trained neural network. And so you have to choose between all of these options. You have to tune your step size. In the end, what you do is you try to initialize a lot of jobs. You try to train the network using different parameters, and eventually maybe one of them works. And people sometimes call this procedure the graduate student descent. So it really takes a lot of time from graduate students to search for all the parameters in order to find a parameter for the training algorithm to correctly train the neural networks for a new setting. And after doing this for a while, as a graduate student, you might not be very happy about it. You might want to have a better way of selecting these parameters, or maybe you are even more ambitious. Instead of just selecting parameters for existing algorithms, you want to automatically discover these new tricks that will improve the convergence of your training process. Can you actually do that? Well, turns out to some extent you can. You can do that using an approach called learning to learn. So there's this very interesting paper with an interesting title called Learning to Learn by Gradient Descent by Gradient Descent. So what the paper tries to do, right, is to use a meta-learning approach to learn a new optimizer. So instead of using all of these standard optimizers and tune the parameters by hand, you actually train a new optimizer that's going to be that's going to perform very well on your data. And this line of work has So there has been a lot of papers in this line of work, and people were actually able to train optimizers that outperform traditional optimizers in practice. So what exactly is this meta-learning approach? Well, in this meta-learning approach, your goal is to optimize the objective function f of w for a distribution of tasks for the tasks that you are interested in. So you are not only interested in optimizing a single objective function, but you are optimizing a distribution of objective function for many, many different tasks. For example, you can think of a distribution of image classification tasks, things that people typically do in this meta-learning approach is, for example, you have your standard data set like CIFAR10 or ImageNet. CIFAR10 has 10 classes, ImageNet has 1,000 classes. You can sample, let's say, half of the number of classes and use that as one of the tasks you are thinking about. And you can define your objective function as what is your prediction accuracy for the subsampled class. So these are some typical distribution of tasks. Of course, people have also considered to optimize over a much broader distribution of tasks that ranges through actual neural network training to simple least squares optimization. So once you have the distribution of tasks, how do you find a better optimizer? How do you learn a better optimizer using gradient descent? So here's the idea, the high-level idea is simple. So you want to abstract your optimization algorithm as an optimizer with some parameter theta, and you will optimize this parameter theta for this distribution of task. So just following this figure, you can see that the optimizer, you can think of it as a box with a parameter theta. What does this box do? Well, this box takes some information about the parameters of the current point, or sometimes also the history of the optimization. So it takes the current point, w, the function value f at current point, the gradient of f at current point, and also possibly all kinds of historical information about, say, average gradient, average function value, and so on. Based on all of these information and the parameter theta, the optimizer is going to output a direction where you want to move, say delta of w. So once you have this delta of w, you can just move to your next point. The next point, w prime, is just going to be the current point w plus this delta of w. And of course, the optimizer can be very simple. If the optimizer is just gradient descent, this delta of w is just going to be equal to minus the gradient of f of w times the step size. But the optimizer can also be very, very complicated. The optimizer can itself be a neural network that just takes all of these input and produces a delta of w. So in the case of stochastic gradient descent or stochastic gradient descent, there's only going to be a single parameter theta, which represents the step size, and the direction is always in either the gradient of f of w or the stochastic gradient at that particular iteration. But in this meta-learning approach, people more often actually use a very complicated optimizer that involves multi-layer neural networks and use this neural network to actually compute what is the next point that you want to go to. Okay, so that's the learning to learn approach. But once we have this optimizer, the real problem is, well, we just say that we want to optimize the parameter theta for this distribution of task. But how do we actually do that, right? How do we find the best parameter theta that's suitable for this distribution of task? Well, this is actually fairly complicated. So in order to train an optimizer, what you need to do is to first unroll the optimizer for a particular instance. So what do I mean by that? Well, so first you sample a function f from your distribution of task. You sample a task that you want to learn. And for this task, you start from some random initialization W0. You feed this random initialization into the optimizer. Optimizer suggests that you go to W1. And then you repeat this procedure. Optimizer is going to tell you to go to W2. You keep going until you have done T steps of the optimization procedure and you reach WT. And then you can, now you have a trajectory of the optimizer. So the optimizer told you to go from W0 to W1 to W2 all the way to WT, right? You have the trajectory of the optimizer for T steps. Now you can define a meta-objective over the trajectory. What would a typical meta-objective look like? Well, for example, it can just be, I want WT to have low loss, so I want to minimize f of WT. Or maybe that's not, maybe that's too noisy. So maybe I want to minimize the average loss over this trajectory. So I can also try to minimize the average loss of f of W0, f of W1, all the way to f of WT, right? So you can think of all kinds of ways to define a meta-objective. And once you have the meta-objective, you can, of course, evaluate the meta-objective over this trajectory. But in addition to that, you can also take the gradient of the parameter theta with respect to this meta-objective. So that gradient with respect to the theta parameter in the optimizer is what we are going to call a meta-gradient. We call it a meta-gradient because it is a gradient for the optimizer theta. So this is to differentiate from the gradient of the objective function f. So once you compute this meta-gradient, you can just do meta-gradient descent on the optimizer parameter theta. And that's why the first learning to learn paper using neural networks is called learning to learn by gradient descent by gradient descent. You use meta-gradient descent to learn a better optimizer that allows you to do gradient descent faster. Unfortunately, well, it's easy for me to say you just compute this meta-objective and do this meta-gradient, right? But if you think about this procedure, this meta-gradient is actually going to be very complicated because this parameter of optimizer theta, once you change that, it's going to change what is the point W1, and then the input to the next level changes. So W2, the change to W2 is going to be even more complicated. And when your meta-objective is defined as, let's say, f of WT, it is actually a very complicated procedure of how this parameter theta changes your meta-objective. It is very similar to doing the gradient for a recurrent neural network, because you can think of this optimizer as one layer of your recurrent neural network. So all of these layers share the same parameter theta. And when you do the gradient, the theta actually influences all of the steps in your optimization. Or you can also think of this as very similar to doing a policy gradient in a reinforcement learning setting. In both of these two cases, it's known that optimization is actually very difficult for both recurrent neural networks and policy gradient. They are not as easy to optimize as standard supervised learning settings. So what are the challenges in this approach? There are actually a lot of challenges, and both theoretically and empirically. It's very hard. So you might think that now we have this approach. As a graduate student, you can just run this approach and let it run, and it will pick the best optimizer for you. Unfortunately, we are not there yet. To run this learn-to-learn approach, you actually need to tune even more parameters to make the learn-to-learn approach work. And that's unfortunate. So what are the challenges? Why do we need to actually tune more parameters for this learn-to-learn approach to work? There are a few things. So first, when you are doing the meta-gradient descent, very often there's going to be a meta-gradient vanishing or meta-gradient explosion problem. So this We know that in traditional supervised learning or in feed-forward or convolutional neural networks, these problems have been largely solved. But unfortunately, for these, because of the recurrent nature of these meta-gradient, the gradient vanishing and explosion problem are much more common for the meta-learning. The meta objective is also a much more complicated objective to optimize. There are possibly many bad local minimum, and that's something that we need to worry about. And even if you were able to train a good optimizer, one thing that you might worry about is whether this optimizer gives you good generalization performance for the original task. Because what this optimizer is trained to do often is to make the training procedure as fast as possible, but but that does not necessarily imply that for your original task, the generalization is going to be good. And finally, of course, this type of approach is actually very hard to analyze, and there are basically no theoretical guarantees on the trained optimizer or on the training process. What do I mean by these two different aspects? Well, by theoretical guarantee on the trained optimizer, I mean that if you train an optimizer, that is a neural network, this optimizer you can then apply to all kinds of tasks, right? You can apply it to a convex optimization task. You can apply it to optimizing a neural network. But in none of these cases, we know any convergence guarantee for the trained optimizer. We don't know how many steps you need to run this trained optimizer in order to solve the optimization problem. We don't even know whether it will converge or not. It's actually quite possible that if you run it on some tasks that you haven't trained before, it can actually diverge, right? And there's also no theoretical guarantee on the training process. So if I do this meta-gradient descent, will I be able to find the optimal optimizer? There's certainly no guarantee on that. And these are very difficult theoretical problems because even without training these neural network optimizers, even for gradient descent optimizers, we don't really know how fast they converge and why they generalize for standard supervised learning problems, right? So in this work, we are going to start from a very simple model for this learning to learn approach. We are going to analyze very simple optimizers, in particular gradient descent and stochastic gradient descent. And we are also going to analyze these simple optimizers on simple objectives. Most of our objectives are going to be quadratic. So we have a bunch of results for these simple settings. So first, for gradient explosion vanishing problem, we show that if you define your meta objective naively, then meta gradient explosion vanishing problem almost always happen. And so your training will get stuck or diverge. So to solve that problem, we can actually design a better meta objective whose meta gradient remain polynomially bounded, so meta gradient explosion vanishing does not happen. However, things are not that easy because even for the new objective, if you are not careful about how you compute the meta gradient, typically the way you compute the meta gradient is you just evaluate your meta objective function and use auto differentiation that's built in from all of these machine learning frameworks. And all of those frameworks use backpropagation to compute the meta gradient. Unfortunately, even if you use this new object that we defined that does not have exploding or vanishing meta gradient, computing the meta gradient directly using backpropagation still does not work because it requires you, we'll explain this later, but it runs into some numerical issues and you still cannot get a reasonable meta gradient. We also study the problem of generalization for trained optimizers. So in this case, we use a least squares objective. So what we can show is when the number of samples is small, you cannot just define your meta objective on your training set. If you do that, you are going to overfit, and the trained optimizer is not going to have good generalization performance. Instead, you need a technique that was introduced last year. So you need to define meta objective on a separate validation set. We will get into that, get into details later. On the other hand, if you have a lot of training data, if you have a large number of training samples, you don't need to define your meta objective on a separate validation set. You are just fine by defining your meta objective on the training set as the earlier approaches. Now let me get into the result. So how can we optimize the step size for a simple quadratic objective? So here the setting is very simple. The objective is just a fixed quadratic objective. It's an objective with on W, which is just the quadratic form W transpose HW. And the algorithm that we use to optimize this objective is also very simple. We will just consider gradient descent for the stock, although in the paper we can also consider stochastic gradient descent. So for gradient descent, and even for gradient descent, we are using a simple version where you use a constant step size. Of course, you can think of running gradient descent with a step size schedule that is not a constant, but that's not what we're going to consider. So what would be the naive meta objective here? As I mentioned, it's very typical to define your meta objective to just be the loss at the last step. So here, what do I mean by that? So this point W of eta t is the point W at the tth iteration with step size eta. So if I run gradient descent with step size eta and I run that for t steps, the point that I get to is called W of eta t. And so objective F evaluated at this point is going to be my meta objective. The meta objective is a function on the parameter eta, which is the step size for the gradient descent algorithm. So what we can prove is that for this objective, if you just directly do meta gradient descent, it's not going to work. For almost all values of eta, the meta gradient in this case, since it's a single parameter, it's just a derivative of f at this point eta is either exponentially large or exponentially small in this number t, where this number t is the number of unrolled steps in the optimization. This is actually fairly easy to prove because we have a quadratic objective. Without loss of generality, we can assume this matrix in the quadratic objective is diagonal because you can always rotate things, and gradient descent is invariant to rotation. If you let lambda I to be the ith diagonal value of h and ci to be the ith coordinate of your initialization, you can actually compute the meta gradient directly. And here is the formula for computing the meta gradient. You don't need to fully read this meta gradient. What is important is to notice that in the very end, there is a exponential term that's 1 minus eta times lambda I to the power 2t minus 1. Okay, so when eta is very large, when eta is large so that 1 minus eta lambda I, so for one of them, 1 minus eta lambda I has an absolute value larger than 1, then this gradient is going to be exponentially large, and your meta gradient descent is going to diverge. But when eta is very small, all of this 1 minus eta lambda i's are going to be bounded away from 1, like all of them have absolute value that's strictly smaller than 1, then this meta gradient becomes exponentially small, and your training essentially becomes stuck. So how do we design a better meta objective? Well, the idea is, in this case, the meta gradient is large, not because, like the main reason that the meta gradient is large or small is because the objective itself is exponentially large or small in the number of unrolled steps. So we all know in the quadratic case, if you use a constant step size, you either diverge exponentially or you converge exponentially. So your final meta objective is going to be exponentially large or small, and that's why the gradient itself is kind of going to be proportional to that. So in order to solve this, we can try to make this range more reasonable by taking a log of the meta objective. So our new meta objective is going to be just 1/t times log of the original meta objective. This 1/t is just there for normalization. Whether you have that or not does not really change the result because it's just a polynomial factor. For the new objective, we can show that the meta gradient is always polynomial in all relevant parameters. So why is that? Well, intuitively, the derivative of the new meta objective has two terms. One is the derivative of, you can compute this by dg over df times the derivative of f itself. It turns out that both terms are either exponentially large or exponentially small, but in all of the cases, they will cancel each other, and the final result is going to be bounded by a polynomial. Unfortunately, this formula that I wrote, computing g, the derivative of g using the product of these two, this is exactly how one would compute this derivative using backpropagation. Since we are relying on since these two terms are both exponentially large or small, and we are relying on them to cancel each other, we are basically trying to compute the ratio of two exponentially large numbers or two exponentially small numbers. And it's well known that when you do that, you run into numerical issues. But we can solve that by actually write a closed form formula for the meta gradient and implement that directly. So with the correct implementation of this derivative, meta gradient descent with a meta step size of 1/100√k, of course, this constant 100 does not really matter too much in theory. This will converge both in theory and in practice for our simple problem. So here's some empirical verification. This is the training trajectory for meta gradient. The blue curve is if you compute the meta gradient correctly using a closed form formula, then meta gradient descent actually converges to the optimal step size for this particular problem. On the other hand, if you just implement this meta gradient descent on a standard deep learning framework such as TensorFlow, then because of numerical issues, you actually get stuck at a suboptimal step size. So the right figure is a similar experiment. If you compute the meta gradient correctly using the closed form formula, no matter what your t is, it will always converge to the correct optimal step size. But if you use the standard implementations, then it will run into numerical issues in many cases. So here, of course, gradient descent is more subject to these numerical issues. RMS prop actually tries to normalize the norm of the gradient, so it makes things a little bit better, but even RMS prop starts to fail when your unroll length is larger. Okay, so our next result is going to be about generalization of trained optimizer. Do we take questions now, or should I wait for questions at the end? Okay, if there are no questions, I'm going to talk about our second set of results, which is generalization of trained optimizer. So in this case, the setting is slightly different, but it's also simple. It is a simple least squares problem where y is equal to w star transpose x plus a noise. W star, for normalization, just consider w star to be a unit vector, x to be a standard spherical Gaussian with variance 1 in every direction. And this noise is also a Gaussian with variance sigma squared. We will later see what the sigma squared is going to be. It's going to be a constant. The objective we use is the typical objective that you would use for a least squares problem, which is the squared loss, right? So f of w is just the squared loss as the average of over all n training data points. So the algorithm we use is also very simple. It's going to be the gradient descent, again with constant step size. We have similar results for Stochastic gradient descent. And here, as I mentioned, we are going to consider two ways of defining the meta-objective. One is to define meta-objective on the original training data, and one is to define it on a separate validation set. So let me be more precise about these two ideas. So let W of eta t, this is the same notion as before, W of eta t be the point W at the tth iteration of gradient descent with step size eta. The first approach that we are going to call the train-by-train approach. So this is the original approach used in the original learn-to-learn paper. So this is the approach that you would directly think of, right? This is perhaps the most natural approach. You will define the meta-objective on the training set. That means you can simply choose the meta-objective as your objective function evaluated at this loss point. And this is very similar to what we did before, and this is perhaps the most natural thing you would do. But another approach called train-by-validation was proposed later. And what train-by-validation does is instead of trying to evaluate the performance of this last point on the original training set that it's trained on, you use a separate validation set that's samped independently from your distribution, and you define your meta-objective as the average loss on this new validation set. Notice that here it's important that this blue color W eta t only depends on the training set, which is independent of the red color variables. The red color variables x prime I and y prime I are sampled independently of the original training set. Okay, so these are the two ways of defining the meta-objective. One we are going to call train-by-train, and the other we are going to call train-by-validation. So what can we show in this case? When do we need train-by-validation? And if we do, when do we need that? We actually have a complete characterization for the least squares setting that we are in. So we can show that when sigma is a large enough constant, and when the number of samples is a constant fraction of the number of dimension. So this is not a typical setting of least squares. So in this setting, your number of samples is smaller than your number of dimensions. Usually in least squares, you want your number of samples to be larger than your number of dimensions. In this case, let's say think of n is equal to d over 2. Then train-by-validation is actually better. We can prove that train-by-validation achieves a much lower generalization error compared to train-by-train. On the other hand, if your number of samples n is much larger than the number of dimensions, say n is at least d log d, then train-by-train is actually close to the minimax optimal solution, so you cannot do better than that. In that case, you do not need to use train-by-validation, you can just use train-by-train. So notice that the case when the number of samples is smaller than the number of dimensions might seem a bit strange for a least squares problem, but this is actually where a typical neural network would operate on, because typically neural networks are very over-parameterized. The number of training parameters is going to be much larger than the number of data samples you have. And in the least squares settings, this really corresponds to the case when the number of samples is much smaller than the number of dimensions. So this really suggests that if you have an over-parameterized neural network and you want to use the meta-learning approach, you should use the train-by-validation objective function. So here's some simple proof idea for this comparison. When you have a large noise and when you have fewer samples, what happens is actually so here's the 0 point, and W star is the optimal solution. So train by train is going to vary train by train because it tries to minimize the training objective. And the training objective in this case is going to be 0 because your number of samples is smaller than the number of dimensions. And when you have fewer equations, then the number of variables, in most cases, you can find an exact solution. So train by train is going to find the empirical risk minimizer, which happens to be very far from W star in this case because of the noise. Because W star actually will not satisfy these equations due to the noise. So in this case, what you need to do traditionally is to have a very strong regularization. You can have a strong regularization on the norm of your solution, or you can do a regularization in the sense of early stopping. Using either regularization, what your algorithm would do is to go a small distance towards this empirical risk minimizer. So you don't go super far, you just go enough distance to decrease your distance to W star. Train by validation, we show is going to be able to catch, to select a step size that's small enough that effectively you are using an early stopping regularization. Because if you use a very small step size, you are not going to go very far, and that is in some sense equivalent to an early stopping regularization. And it will perform much better than the empirical risk minimizer in this large noise case. On the other hand, when you have a small amount of noise and when you have a lot more samples, what happens is that in this case, the empirical risk minimizer itself is actually very good. It is almost minimax optimal for the least squares problem. So in this case, both train by train and train by validation approach are going to converge to this empirical risk minimizer, and you will not see a difference between them. Okay, so we also run some experiments verifying these results. So first, we try to run verify these results on the original least squares model that we proposed. As you can see on the left figure, the blue plot is the performance of train by train, and the red curve is the performance of train by validation, and the left figure is a training loss. So as you can see, when the sample size is small, train by train actually achieves 0 training loss. And 0 training loss is actually not good in this case because in this case, your number of samples is too small. Achieving 0 training loss actually means you are overfitting. And when we look at the figure on the right, this is going to be the test loss for train by train and train by validation. And as you can see, as the sample size, when the sample size is small, train by train has a significantly larger test error compared to the train by validation approach. But as the number of samples grow, the performance of the two becomes the same. So when you have a large enough number of samples, yeah, you don't need to worry about whether using train by train or using train by validation. These are, of course, results only for least squares, but we actually also tried to verify the results on neural network optimizers. These are the more complicated optimizers that were used in the learning to learn approach. Turns out these optimizers have a similar behavior. So let's look at the figures on top. So figures on top is what we did. We trained MNIST dataset using these learned optimizers on 1,000 samples. So as you can see on the left, the training accuracy all approaches 1. But when you look at the test accuracy, the blue curve and the black curve are both train by train approaches using either 1,000 training samples or 2,000 training samples. And you can see the test accuracy are both actually bad as you increase the amount of training time. So they start to overfit. On the other hand, if you run SGD and you tune the step size correctly, it's not going to overfit. And if you use the train by validation approach using 1,000 training samples and 1,000 test samples, or sorry, 1,000 validation samples, its performance is very similar to a well-tuned stochastic gradient descent. And this difference between train-by-train and train-by-validation approach becomes even more clear when you have label noise to the data. So in this bottom figures, we added 20% label noise to MNIST dataset. And as you can see here, in this case, even stochastic gradient descent, the green curve starts to overfit, and the train-by-train curves overfit even more. On the other hand, the train-by-validation approach still gets a reasonable test accuracy. So this is a different set of comparisons. So the top figures remain the same. It's still training MNIST dataset with 1,000 samples, but the bottom figures, we will actually train MNIST with all of the samples, and we do not add any label noise. So the bottom figures have a much larger number of samples. And as you can see, as the number of samples is very large, both approach and the original stochastic gradient descent actually perform similarly, and none of them actually overfits. So just to conclude, in this paper, we have several initial results for the theoretically understanding the learning to learn approach. So I see there is a question. Let me just quickly finish the conclusion and I will get to the questions. So we showed that choosing meta-objective carefully can possibly alleviate gradient explosion and vanishing problem. But even if you can do that, you need to be careful with backpropagation because you might still run into numerical issues. We also show that when there are fewer samples or more noise, you need to use the train-by-validation approach. You need to define your meta-objective on a separate validation set. But in terms, there are still a lot of open problems in this direction. So first, our new meta-objective only works for quadratic optimization. So can we alleviate the gradient explosion and vanishing problem or the numerical issues, not only for quadratic objectives and for gradient descent? Can we do that for neural network objectives and also neural network optimizers? Also, can we tune the parameters for more complicated optimizers? Of course, the neural network optimizers would be very hard to analyze, but even if we are able to tune the parameters for somewhat more complicated optimizers like Adam, that might still be valuable in practice. Thanks. So I see one question, so maybe let me first answer that.
Let me read it for you because we have other audience from Bilibili.
Okay, yeah.
Yeah. So, but there are actually quite a few other questions. Let me just read them in order, okay?
Okay, yeah. Okay. Thanks.
So the first question, so the original question was in Chinese, and so let me just translate it. So the first question is, are there any other prior knowledge besides learning to learn that can be used to speed up the training?
Are there any prior knowledge besides learning to learn that can be used to improve the speed of training? Yes. I mean, in fact, there are a lot of prior knowledge, right? Because for example, in the supervised learning setting, if you have a feed-forward neural network or if you have a convolutional neural network, there are different initialization schemes. And if you initialize things in the correct scale, that will significantly improve the training performance. And also we know that if you run gradient descent or stochastic or Adam using the recommended parameter, it works very well for together with these networks. So a lot of these prior knowledge or common wisdom are already built into these machine learning frameworks. What's difficult is when you move to a completely new domain, right? For example, if you are familiar with training supervised learning problems, but you are now trying to train again or something like that, then things become more complicated.
Okay. So the second question is that, can this method solve other gradient vanishing problems?
Right. So can this method solve other gradient vanishing problems? So it is possible, but we don't have such result. It really depends. So in our case, the gradient vanishing problem happens because the objective function itself is actually exponentially small. So if you have another setting where the reason that gradient vanishing happens is very similar, then it is possible that the same approach would work. On the other hand, there could be other reasons for gradient vanishing. For example, maybe your activation, maybe let's say you used a sigmoid activation and you happen to be at the two ends of the sigmoid, then your gradient is also going to vanish. In that case, your objective function is not small, and I don't think our approach is going to work there.
Okay. So the third question is meta gradient optimization good for defending adversarial or not?
Oh, is meta gradient optimization good for adversarial defense? So I think that really depends on how you define your meta objective. I would assume if you just naively define your meta objective as the original loss function, that probably is not going to do anything in terms of adversarial robustness. But you can certainly try to change your meta objective, right? You can even change your meta objective to be a robust version, like a robust loss for the point that you end up at. I don't know of any empirical experiments on that, but at least it has the chance of providing some robustness to adversarial attacks.
So the next question is how to come up with such a meta objective? Are there some general methodologies?
Right. How to? I mean, usually it's just what you want to optimize, right? So coming up with a meta objective, as we see in the talk, the meta objective we have in the talk are all fairly simple. They are just some functions on the last point, right? Of course, for our new meta objective, we took a log transformation of that. But the motivation is really because we don't want this meta objective to have a very large range, right? We want the range to be polynomially bounded. In general, people have tried different ways of coming up with meta objectives. They can either be the last point or the average point, or in practice, people actually also slowly increase unrow length in order to make the training process more stable. So there are a lot of tricks in defining these meta objectives, although most of them are intuitive. So if you want to know how people actually do this, I recommend reading this paper by Metz et al. At 2019.
Okay, so then be this question. So I guess this is why, right? Why TVB outperform SGD1? The samples are noisy. Are there any intuitive explanations?
Right. So why does it perform better when the samples are noisy? That's because the train-by-train approach actually in this least square setting always converges to the empirical risk minimizer. And what happens, let me go to the figure. What happens when there's more noise is this empirical risk minimizer is actually a very bad solution. So you can think if the noise is zero, the empirical risk minimizer is going to be exactly equal to W star, or I should No, that's actually not exactly true. In this case, the number of samples is smaller than the number of dimensions. So the number, so there are multiple empirical risk minimizers, and they form a subspace. The one that you would find is the one that's in the span of the data. But at the very least, when you have no noise, W star is one of the empirical risk minimizers. But what happens when you add noise is that W star is no longer a empirical risk minimizer because W star does not have zero loss. If we look back at this model, if W is equal to W star, Yi minus W star transpose Xi is going to be this.
Okay,
yeah,
actually, that was the last question.
Okay.
So you can, maybe you can finish that question. And...
Right. So I was just explaining that in the large noise case, and when you have fewer samples, the empirical risk minimizer is actually very bad, and that's why train by train is also very bad. But train by validation, because it evaluates the performance on a separate validation set, is able to see that the empirical risk minimizer is actually very bad, and you should use a like it automatically applies an early stopping regularization and achieves a much better result.
Mm-hmm. Any other question from the Zoom? So if there are no further questions, okay, so you got the answer. Okay, so if there are no further questions, let's thanks Jerome for the nice talk again.